We cannot prove we are the first civilization on Earth, not because the evidence says we aren't, because the evidence doesn't exist either way. The geological record older than a few million years simply cannot distinguish between a volcanic event and an industrial one. 2 NASA scientists said that out loud in 2018 in a peer-reviewed journal and then went looking anyway. What they found is what tonight is about: a 56-million-year-old carbon scar, a comet that may have erased an entire chapter of human history 12,800 years ago, a temple in Turkey older than agriculture, and a desert monument battered by rainfall that hasn't fallen in 9,000 years. So go ahead, get comfortable, hit subscribe if you have not, and let's slowly get into this. Part 1. The moment science blinked. In April of 2018, inside one of the most respected scientific institutions on the planet, 2 researchers sat down and asked a question that almost no one in their field had dared to ask out loud. Not because it was stupid, not because it was fringe, but because the answer was genuinely uncomfortable, and in science, genuinely uncomfortable answers have a way of making careers very short. The institution was NASA's Goddard Institute for Space Studies in New York City, not exactly the home of conspiracy theories. The researchers were Adam Frank, an astrophysicist at the University of Rochester, and Gavin Schmidt, a climate scientist who at the time was the director of NASA GISS itself. These are not people who wear tinfoil hats. These are people who publish in peer-reviewed journals, who sit on federal advisory panels, who appear in university textbooks. And the question they asked was published in the International Journal of Astrobiology, which means it went through rigorous academic review before anyone was allowed to read it. So what was the question? It wasn't, did an advanced civilization exist on Earth before humans? That would have been too easy to dismiss. It was something far more unsettling. The question they actually asked was, if an industrial civilization had existed on Earth millions of years before us, would we even be able to detect it? Read that again slowly, because that distinction matters enormously. They weren't claiming anything existed. They were asking whether we would know if it did, and their answer, carefully, methodically, with full citations and no drama, was essentially no. Not definitely no. Not provably no. But no in a way that should make you pause for a long moment before you go back to assuming the answer is obvious. They called it the Silurian hypothesis, a name borrowed from a 1970 Doctor Who episode featuring a race of intelligent reptiles who evolved on Earth before humans and retreated underground when a catastrophe hit. The scientists were aware of the irony, and they used it deliberately, not to invoke science fiction, but to signal that they understood how strange the question sounded, and that they were asking it anyway with full scientific seriousness. When researchers name their own hypothesis after a Doctor Who episode, they are telling you something. They are telling you they know this looks weird, and they're doing it anyway because the data compelled them to. Here is the core of what they found. The geological record, meaning the layers of rock, sediment, ice cores, and chemical signatures that scientists use to reconstruct Earth's past, becomes increasingly unreliable the further back in time you go. Not gradually unreliable, not smoothly unreliable, but unreliable in specific, predictable ways that happen to correspond exactly with the kinds of signatures an industrial civilization would leave behind. Think about what an industrial civilization actually produces. It produces carbon dioxide, it produces methane, it produces trace heavy metals, synthetic organic molecules, isotopic anomalies in the carbon record, novel radioactive isotopes that don't occur naturally in significant concentrations, and a thin layer of materials, plastics, alloys, refined compounds that have no natural analogue. If you were a geologist from another planet arriving at Earth 1 million years after we were gone, looking for evidence that we existed, those are the fingerprints you would search for. Now ask yourself how long those fingerprints last. The carbon spike from burning fossil fuels would persist in the rock record for somewhere between 10,000 and 100,000 years depending on conditions, A blink of time by geological standards. Plastic degrades. Synthetic molecules break down into simpler compounds that look increasingly like natural organic chemistry as the millennia pile up. And the deeper you go in the rock record, the more compression, heat, chemical exchange, and tectonic activity has processed those layers, smoothing them, transforming them, sometimes erasing them entirely. Adam Frank and Gavin Schmidt weren't saying a prior civilization definitely existed. They were saying something more philosophically interesting than that. They were saying that science, as currently practiced, with the tools we currently have, cannot rule it out for any period before roughly 1 to 2 million years ago. And since the genus Homo has only been around for about 2.8 million years, and anatomically modern humans for only around 300,000 years, that window of undetectable history is enormous. Millions of years of planetary time during which something could have risen, industrialized, collapsed, and been erased without leaving a recoverable signature. What makes this remarkable is not the claim, it's the honesty. For decades, scientists had avoided asking this question not because they thought it was frivolous, but because asking it gave oxygen to exactly the kind of fringe speculation they spend enormous energy trying to push back against. If a NASA scientist asks whether ancient civilizations could have existed without leaving evidence, the next morning every tabloid and conspiracy website on the planet runs a headline saying NASA confirms lost civilization. So the question just didn't get asked. It sat there in the space between obviously impossible and scientifically unaddressable, and no one touched it. Frank and Schmidt touched it, and in doing so, they didn't open a door to pseudoscience. They actually did the opposite. They drew a precise, careful line between what science can confidently claim and what it cannot. Certainty about the absence of something requires evidence of that absence. And when the mechanism that would preserve that evidence is also the mechanism that destroys it, you don't have certainty. You have assumption. Here's where the emotional weight of this lands, and I want you to sit with it for a moment. We go about our lives with a background assumption that is so fundamental we never examine it, that we are the first intelligent species on this planet to build cities, to harness energy, to reshape ecosystems on a global scale. That assumption feels so obviously true that questioning it seems almost laughable. And yet 2 mainstream scientists publishing in a peer-reviewed journal just told us that we cannot confirm it for any period beyond roughly 1 million years ago. The science isn't hiding evidence of a prior civilization. The science is admitting it cannot look back far enough to rule one out. And that admission, quiet, academic, buried in a journal that most people have never heard of, changes something about how the question feels. Because the question now isn't whether we have proof. The question is what it means that proof, in either direction, may be permanently out of reach. And that brings us to the actual mechanism behind this. The real reason we can't look back and see clearly isn't just the passage of time. It's something much more active than that. It's the planet itself. A geological system of almost incomprehensible violence and scale that doesn't preserve the past so much as it systematically devours it. Part 2. The planet that deletes its own memory. Earth is not a museum. That's the first thing you have to understand if you want to grasp what we're actually dealing with here. We tend to think of the planet as a stable backdrop against which events unfold, a stage that records what happens on it, accumulates layers, and holds them for future discovery. That is almost exactly backward. Earth is not a recording device, it is a processor, and what it processes, over millions of years, is itself. Start with plate tectonics. The continents are not fixed. They are fragments of crust floating on a mantle of partially molten rock, moving at speeds of roughly 2 to 10 centimeters per year, about as fast as your fingernails grow. Over millions of years, that slow drift rearranges everything. Oceans open and close. Mountain ranges rise and are ground down to nothing. And critically, the ocean floor, the part of the crust that covers roughly 70% of the planet's surface, is continuously recycled. Oceanic crust forms at mid-ocean ridges where magma wells up from below, spreads outward, and eventually gets pushed back down into the mantle at subduction zones on the far side. The average age of oceanic crust is around 60 million years. There is almost no ocean floor older than about 200 million years, because it has all been consumed and remelted. Whatever was sitting on top of it, sediment, structures, chemical signatures, anything, went with it. Let's put that in terms of our own history. 200 million years ago is the Triassic period. Dinosaurs were just getting started. Mammals hadn't yet differentiated into anything you would recognize. 200 million years is the entire ceiling of the oceanic geological record, the maximum depth at which we can look for preserved evidence of anything that happened on or near the ocean floor. And for civilizations, that matters an enormous amount, because civilizations don't build in the middle of continents. They build on coastlines, they build on river deltas, they build on the low, fertile ground near water, which tends to be the exact ground that gets subducted, eroded, flooded, and buried. Now add erosion. A mountain range that rises through geological uplift loses material constantly. Wind, rain, freeze-thaw cycles all grind it down at rates of roughly 0.5 millimeter per year, averaged across a surface. That sounds trivial. Over 1 million years, 0.5 millimeter per year removes 500 meters of material from a surface. Over 10 million years, that's 5 kilometers. The Rocky Mountains, the Alps, the Himalayas, these are all being continuously destroyed even as they are still being built. The material that erodes off them washes into river systems, gets carried to lowland basins, and gets deposited as sedimentary layers that bury whatever was there before. Think about that sequence. A coastal settlement, or something far more sophisticated, that existed 60 million years ago would have faced the following process. The sea level around it rose and fell repeatedly as ice ages came and went. If it survived flooding, erosion stripped its surfaces. If it survived erosion, the tectonic forces under it slowly moved it, cracked it, tilted it. Over millions of years, sediment buried it under kilometers of rock. If the sediment happened to be in a subduction zone, it got pushed back into the mantle. If it wasn't subducted, the compression and heat at those depths transformed it through a process called metamorphism, essentially cooking and crushing the rock until the original structure is unrecognizable. We know what this does to things we can actually test, because we've built things and watched what geology does to them over thousands of years. The Roman city of Pompeii was buried under volcanic ash in 79 CE. After roughly 2,000 years, it was relatively well preserved, but only because the burial was rapid, the chemistry was right, and the site happened to be in a geologically stable area. Now imagine Pompeii without the lucky rapid burial, without the stable geology, exposed to normal erosion for 100,000 years, let alone 1 million. You wouldn't find a wall, you wouldn't find a foundation stone. You would find, if you were very lucky, a slight chemical anomaly in the soil and some anomalous concentration of heavy metals that would require sophisticated analysis to even notice. Here's a statistic worth sitting with. Less than 1% of Earth's current surface is urbanized by humans. Less than 1%. And we are the most expansive technological civilization this planet has ever seen, at least as far as we currently know. We have covered the planet in roads, buildings, agricultural fields, communication infrastructure, electrical grids, and all of that together represents less than 1% of the surface area. Now imagine what percentage of a civilization that was less expansive than ours would occupy. And then imagine that percentage, after millions of years of the geological processes we just described, being recoverable in any form. This is what scientists call deep time blindness, and it affects everyone who hasn't spent years working in geology or paleontology. Human intuition is built for timescales of decades, maybe centuries at the outside. We struggle viscerally to comprehend what 1 million years actually means in physical terms. 1 million years ago, anatomically modern humans didn't exist yet. But in geological terms, 1 million years is recent. It's practically yesterday. The geological features that have formed and been erased in the last million years alone would fill volumes. There's another layer to this that doesn't get discussed enough, and it connects directly to the question of where any prior civilization would have actually lived. About 20,000 years ago, during the peak of the last glacial maximum, sea levels were roughly 120 meters lower than they are today. 120 meters. That is a vertical drop equivalent to a 35-story building, and what that means in practical terms is that enormous sections of what is now ocean floor were dry land. The continental shelves, the shallow underwater plateaus that ring most of the world's continents, were exposed and habitable. Doggerland, the land bridge that connected Britain to continental Europe, was a substantial landmass with rivers, forests, and coastlines of its own. The region we now call the Persian Gulf was a river valley. Sunderland, the continental shelf of Southeast Asia, was a landmass roughly the size of India, connecting what are now the islands of Indonesia and Borneo to the Asian mainland. These submerged shelves are exactly where human populations would have been densest during the period immediately after the Younger Dryas, and they are now underwater, poorly mapped, rarely studied, and essentially inaccessible to conventional archaeology. Whatever was there is sitting under the ocean, under sediment, and in many cases under layers of biological reef growth that accumulated over the 10,000 years since flooding. The point is not that a civilization is necessarily buried out there. The point is that the natural tendency of civilizations to cluster in coastal lowlands means that their most likely locations are also the locations that the geological record has most thoroughly erased. Scientists call this information decay. Over time, every signal in the geological record blurs. The sharp edges of an event become gradual transitions. The specific chemistry of a layer gets diluted through mixing with adjacent layers. The unique signature of something unusual starts to resemble the background signature of ordinary geological processes. A carbon spike from industrial activity, given enough time, becomes indistinguishable from a carbon spike from a large volcanic episode. A concentration of rare earth elements from refined metals becomes indistinguishable from a natural ore deposit. The record doesn't lie, exactly, but it stops being specific. It becomes ambiguous in a way that makes interpretation genuinely difficult. So that raises the obvious question. If the record eventually erases everything, what would actually survive? What could a civilization leave behind that would punch through millions of years of geological processing and remain detectable? And the answer, when scientists like Frank and Schmidt actually work through it, is a short and somewhat alarming list. Part 3. The signature problem. If you wanted to search the geological record for evidence of a past industrial civilization, you would be looking for a very specific set of chemical and isotopic fingerprints. Not structures, not artifacts. Those don't survive millions of years. You would be looking for the kinds of large-scale chemical disruptions that only certain processes can produce, the kinds of signals that stand out against the background noise of ordinary geological time, the same way a radio transmission stands out against static. The first and most important of these signatures is a carbon isotope anomaly. Carbon comes in several forms, isotopes, that differ slightly in atomic weight. The most common form is carbon-12. A slightly heavier form, carbon-13, occurs in consistent ratios in most natural carbon reservoirs. But fossil fuels, coal, oil, natural gas, are depleted in carbon-13 relative to the normal ratio. They formed from ancient organic matter over millions of years, and organic processes preferentially incorporate carbon-12. So when you burn fossil fuels, you inject large amounts of carbon-12 into the atmosphere and ocean system, which shifts the ratio of carbon-12 to carbon-13 in a measurable, distinctive way. Geologists call this a negative carbon isotope excursion, and it shows up clearly in the rock record wherever it occurs. The second signature is rare earth element concentration. Industrial processes, mining, smelting, manufacturing, concentrate elements that occur naturally at very low levels in Earth's crust. If a civilization extracted and processed significant quantities of certain metals and distributed them across the environment through waste, pollution, and general industrial activity, you would expect to see anomalously high concentrations of those elements in a geological layer corresponding to that period. The third signature is synthetic organic molecules. We produce enormous quantities of compounds that don't occur in nature: chlorinated hydrocarbons, polychlorinated biphenyls, various plasticizers and solvents. Some of these compounds are remarkably persistent. PCBs, for instance, have half-lives measured in decades to centuries in some environments. Whether any trace of them would persist for millions of years is unclear, but they represent in principle a detectable marker of industrial activity. The fourth, and perhaps most interesting signature, is isotopic anomalies in certain radioactive elements. We have produced plutonium, americium, and other transuranic elements through nuclear reactions that essentially do not occur in nature. The specific isotopic signatures of reactor-produced and weapon-produced nuclear materials are distinctive and unambiguous. In principle, trace amounts of these could persist in rock layers if the conditions were right, though degradation over geological time is a serious obstacle. Now here is the paradox that makes this entire question so interesting and so genuinely unresolved. Almost every one of those signatures has a natural analogue that is difficult or impossible to distinguish from the artificial version when you're looking at it through the filter of millions of years of geological processing. Carbon isotope excursions happen naturally. Large volcanic episodes inject enormous quantities of carbon into the atmosphere and can produce negative isotope shifts similar to those from fossil fuel burning. The organic decay of massive quantities of vegetation, or the destabilization of methane reservoirs on the ocean floor, can produce similar signatures. Rare earth element concentrations occur naturally through hydrothermal processes that concentrate metals in exactly the kinds of patterns that might mimic industrial extraction and dispersal. Organic chemistry is so varied and complex that distinguishing a degraded synthetic molecule from a naturally occurring analogue after millions of years of chemical transformation is, at best, extraordinarily difficult and at worst, simply impossible. And here's the part that stops you cold when you think about it carefully. The cleaner a civilization is, the less it pollutes, the more efficiently it uses energy, the more carefully it manages its waste streams, the smaller a signature it leaves in the geological record. A civilization that developed renewable energy early, that never went through a phase of mass fossil fuel combustion, that managed its rare earth extraction efficiently and contained its chemical waste. That civilization might leave almost no detectable signature whatsoever. It might leave, as Frank and Schmidt put it in their paper, a whisper rather than a shout. And a whisper, after millions of years of geological noise, is silence. What this means is that the detectability problem is asymmetric in a very important and underappreciated way. We would be much more likely to detect a civilization that was roughly as dirty and careless as we are, or dirtier, than one that was cleaner and more advanced. A civilization advanced enough to have solved its energy and pollution problems might be precisely the kind of civilization that is completely undetectable to us. The more sophisticated the civilization, the less trace it leaves, which means our search methodology, such as it is biased toward finding the unsophisticated and failing to find the sophisticated. This brings up a second paradox. The geological record doesn't label its anomalies. When you find a carbon spike in a rock layer, the rock doesn't tell you what caused it. It just shows you the spike. The cause, whether volcanic, biological, orbital, or something else entirely, has to be inferred from the pattern of associated evidence. And associated evidence over geological time tends to be incomplete. This is not a failure of science. It's a consequence of the physical processes involved. You're trying to reconstruct a crime scene where all the fingerprints have been smeared, most of the evidence has been removed, and the building itself has been partially demolished and rebuilt several times since the event. Here is what builds the tension to an almost unbearable point. We are not actually in a position where we have looked at the geological record and found nothing unusual. we have looked at the geological record and found several things that are genuinely, stubbornly, difficult to fully explain with the mechanisms we currently have available. And the most compelling of those anomalies sits at 56 million years ago, a scar in Earth's history so strange and so similar to what we're doing right now that when climate scientists first described it in detail, they called it the closest geological analogue to the modern climate crisis. Part 4. 56 million years ago, a world that shouldn't exist. Picture a world where crocodiles live near the Arctic Circle, where tropical forests extend to latitudes we currently associate with tundra, where the deep ocean, normally cold, oxygen-rich, and biologically stable, has warmed enough in its lower layers to kill enormous quantities of the life that depends on that cold stability. This is not science fiction. This is not a thought experiment. This is a real period in Earth's history, documented in exquisite detail across hundreds of geological sites worldwide, called the Paleocene-Eocene Thermal Maximum. The Paleocene-Eocene Thermal Maximum, scientists abbreviate it as the PETM, occurred approximately 56 million years ago, right at the boundary between two geological epochs, and in geological terms, it was violent. Global average temperatures rose somewhere between 5 and 8 degrees Celsius, within what the rock record suggests was a geologically very short period of time. Estimates range from as little as 6,000 years to as many as 20,000 years depending on the study and the site. To give you a sense of what that timescale means, 6,000 years is the distance from the earliest Sumerian writing to right now. It is all of recorded human history, and within that span, the entire planet's climate system underwent a shift of a magnitude that makes our current climate projections look modest by comparison. Arctic temperatures during the PETM reached approximately 23 degrees Celsius. That's roughly 73 degrees Fahrenheit, warmer than a comfortable spring day in many temperate regions. The Arctic Ocean was, for a period, something like a warm, partially stratified subtropical sea. Fossil pollen and leaf records from Arctic sediments of this period show palms, cycads, and other tropical plants growing at high latitudes. Fossil crocodilians, not the small primitive kind but full-sized animals, have been found in geological formations from Alaska and Ellesmere Island dating to this period. In the tropics, ocean surface temperatures in some regions reached approximately 36 degrees Celsius. That's 97 degrees Fahrenheit, hotter than a hot tub. For comparison, the warmest tropical ocean surface temperatures we see today, in the Persian Gulf during summer, peak at around 35 degrees Celsius, and marine biologists treat that as an emergency for coral reef systems. At 36 degrees during the PETM, the tropical oceans were essentially becoming inhospitable to the cold water fish and marine organisms that had previously dominated them. Entire faunal assemblages collapsed and were replaced. At the deep ocean level, the change was most catastrophic. The deep ocean depends on thermohaline circulation, the global conveyor belt of ocean water driven by temperature and salinity differences between the poles and the tropics. Cold, salty polar water sinks and drives this circulation. When the poles warmed dramatically during the PETM, the density gradient that drives thermohaline circulation weakened and the deep ocean began to stagnate. Oxygen levels in the deep ocean water dropped, a condition called anoxia, and roughly 30 to 50% of deep-sea benthic foraminifera, tiny bottom-dwelling organisms whose fossils we use to reconstruct ancient ocean conditions, went extinct, not declined, went extinct globally. What you're looking at in the PETM is a case study in what happens to a planetary climate system when you inject large amounts of carbon into the atmosphere very rapidly. The Earth has a natural response system. It absorbs carbon through chemical weathering of rocks, through ocean chemistry, through the growth of vegetation. But that response system operates on timescales of tens to hundreds of thousands of years. If you inject carbon faster than the planet can absorb it, the system overshoots. temperatures climb faster than ecosystems can adapt, and the signature of that overshooting is exactly what we see in the PETM record. But here's the part that connects this directly to the central question we're asking tonight, and I want you to hold this in your mind as we go through the detail. The PETM is described by climate scientists as the closest geological analogue to what we are doing with the climate right now. Not a distant analogue, not a rough analogue, the closest one in all of geological history. The rate of carbon injection, the magnitude of the temperature shift, the disruption to ocean chemistry, all of these parameters in the PETM fall within the same order of magnitude as our current trajectory. And in that parallel sits a question that is almost too uncomfortable to look at directly. Because we know what caused our carbon spike. We know exactly when it started, roughly how much we've put in, and what the mechanism is. We can point to the Industrial Revolution, to the combustion of coal and oil and gas, to deforestation and agriculture. The human signature on the modern carbon record is unmistakable, precisely dated, and causally understood. Now apply that lens to the PETM. If someone were to look at the PETM geological record from the outside, with no prior knowledge of what caused it, the signature they would see is almost exactly what they would see if they looked at our modern record. A rapid, large-scale injection of carbon-12 into the global carbon cycle, producing a distinctive negative isotope excursion in the marine sediment record, coinciding with a sharp temperature increase and associated ecological disruption. The question that Frank and Schmidt were brave enough to ask is simply, would we be able to tell the difference? Part 5. The carbon spike that mirrors us. The specific chemical signature of the PETM is called a carbon isotope excursion. In marine sediment cores taken from dozens of locations around the world, the boundary between Paleocene and Eocene rock is marked by a sharp negative shift in the ratio of carbon-13 to carbon-12. Scientists measure this shift in units called per mil, parts per thousand, and the PETM excursion measures somewhere between 2.5 and 7 per mil negative, depending on the location and the method used to measure it. To put that in perspective, the modern carbon isotope shift associated with fossil fuel burning has already produced a measurable negative excursion in the marine record that is tracking very closely to the early stages of the PETM signal. We are, in isotopic terms, drawing the same curve that was drawn 56 million years ago. Our line is newer, shorter, and not yet as extreme, but the shape and direction are strikingly similar. The amount of carbon injected during the PETM is estimated at somewhere between 3,000 and 13,000 petagrams. A petagram is 1 billion metric tons. The total amount of carbon humans have released since the Industrial Revolution is estimated at approximately 580 petagrams, sitting at the lower end of the PETM range. We haven't yet matched the PETM in total magnitude, but we are injecting that carbon faster than the PETM did it. Our current rate of carbon emission is estimated to be roughly 10 times faster than the peak injection rate of the PETM. We are doing in centuries what the PETM did over thousands of years, and this is where the science gets genuinely complicated, because the PETM did not have us burning coal to produce it. Something else caused it, and the honest scientific answer to the question of what that something else was is, we're not entirely sure. The leading candidate is volcanism. About 56 million years ago, a massive volcanic episode was occurring in what we now call the North Atlantic Igneous Province, a region spanning parts of Greenland, Iceland, the British Isles, and the adjacent ocean floor. This volcanic episode, associated with the opening of the North Atlantic Ocean as the continents continued their drift, produced enormous quantities of lava and almost certainly enormous quantities of volcanic carbon dioxide and sulfur gases. The Deccan Traps volcanism in what is now India, which occurred a few million years earlier around the time of the mass extinction that killed the non-avian dinosaurs, gives us a sense of the scale of carbon release that flood basalt volcanism can produce. The problem with the volcanic explanation for the PETM is that it doesn't fully work. The volume of volcanic rock we can identify from the North Atlantic igneous province during this period doesn't obviously match the scale of carbon injection required to produce the PETM. Some researchers have proposed that volcanic intrusions, magma baking through organic-rich sedimentary rocks on the seafloor, could have released carbon directly from those sediments as well as from the magma itself, significantly multiplying the effective carbon output. This is plausible, and it may be part of the answer, but it introduces additional uncertainty rather than resolving the question neatly. The second major candidate is methane hydrate dissociation. Methane hydrates are ice-like compounds where methane, a potent greenhouse gas, is locked in a crystalline water structure on the deep ocean floor under high pressure and low temperature. If the deep ocean warms enough, these compounds can become unstable and release their methane suddenly into the water column and atmosphere. A large enough release of methane from ocean floor hydrates could produce exactly the kind of rapid, carbon-12 enriched carbon injection that would match the PETM signature, because methane from hydrates is biogenic in origin and therefore depleted in carbon-13. The problem with the methane hydrate explanation is that it's a feedback mechanism, not a trigger. Something has to warm the deep ocean enough to destabilize the hydrates in the first place, and that something, whatever initial warming event caused the chain reaction, is itself unexplained. So the current scientific picture of the PETM, after decades of intensive study and hundreds of research papers, is roughly this: a combination of volcanism, methane hydrate feedback, possibly other mechanisms, all combining in ways that amplified each other and produced a rapid, large-scale carbon injection that no single mechanism can fully account for on its own. It's a satisfying answer in some ways, because it invokes real mechanisms and real geological evidence. But it's unsatisfying in a deeper way, because it still doesn't close the book on exactly what happened, exactly when the trigger fired, and exactly why the PETM was as fast and as large as it was. And here, finally, is where the Silurian hypothesis becomes quietly relevant again. Frank and Schmidt weren't pointing at the PETM and saying, this was caused by a prior civilization. They were much more careful and much more interesting than that. What they were saying is, look at this event, look at the carbon signature, look at the rate of change, look at the associated ecological disruption. Now ask yourself, if this had been caused by an industrial civilization rather than by geological processes, what would we see differently? What evidence would allow us to tell the two apart? And the answer, after you work through the chemistry and the physics carefully, is not much. The carbon isotope signature of a massive volcanic episode is similar enough to the signature of fossil fuel burning that, at the resolution available to us through 56 million-year-old rock, distinguishing them becomes genuinely difficult. Not impossible perhaps for the PETM specifically, where we have enough additional contextual evidence about the volcanic activity to make a reasonable case. But for a hypothetical similar event at a time when we had less preserved context, yes, genuinely and honestly difficult. We would expect the geological record to look, in important ways, similar whether it was caused by volcanic processes or industrial ones. And the question of whether that ambiguity makes us uncomfortable is not a scientific question. It's a philosophical one. It's a question about how confident we want to be in assumptions we've never tested. Part 6. The Unsolved Trigger Problem. Scientific debates about the PETM have been ongoing for roughly 3 decades, ever since the event was first clearly characterized in the early 1990s. In that time, the community has generated a rich and detailed picture of what happened during the PETM, the temperatures reached, the extinctions triggered, the ocean chemistry changes recorded, the geographic distribution of the signal across every ocean basin. What has proven stubbornly resistant to resolution is the question of what, precisely, fired the starting gun. This is not a minor quibble. The trigger question is important because the trigger determines the mechanism, and the mechanism determines how we interpret all the other evidence. If pure volcanism caused the PETM, then the particular pattern of carbon injection, the rate, the isotopic signature, the relationship to other geochemical changes, should be consistent with what we know about how volcanism produces carbon emissions. If methane hydrate destabilization was the primary driver, the isotopic signal should have a specific character that distinguishes biogenic methane from volcanic carbon dioxide. If some third mechanism was involved, orbital forcing, some cascade effect we haven't fully modelled, or something else, the fingerprint would be different again. The difficulty is that these mechanisms are not mutually exclusive, and the geological record doesn't preserve them separately. What we see in a sediment core is the combined effect of everything that was happening during the PETM, all the carbon sources, all the feedbacks, all the secondary effects, averaged together, compressed over thousands of years, and filtered through whatever preservation processes were at work at that specific location. Untangling which thread contributed how much requires modelling that makes significant assumptions, and different modelling approaches produce different answers. The debate in the scientific literature is real, active, and conducted entirely within the framework of normal science. Researchers publish papers arguing for primarily volcanic triggers, others argue for primarily methane-driven scenarios, and most recent work involves some combination of the two operating through a cascade of feedbacks. The Intergovernmental Panel on Climate Change treats the PETM as an important paleoclimate analogue for understanding modern climate change, precisely because the mechanisms, however contested in their exact proportions, involve the same basic physics as modern carbon emissions. What connects this ongoing trigger debate to the central question we're exploring tonight is epistemological rather than empirical. Science is extremely good at characterizing what happened. The PETM is one of the best documented geological events in Earth's history, precisely because of how anomalous and important it is. But the mechanism, the why and the how of the trigger, remains genuinely uncertain, and in that uncertainty sits the very point that Frank and Schmidt were making. The geological record tells us about effects. It tells us about the scale and speed of changes. It is much less reliable at telling us about causes, especially when the causes are processes that themselves left ambiguous or degraded evidence. This is not a failure. This is just the nature of looking backwards through time at events that happened before humans existed to observe them directly. Every conclusion about the deep geological past is an inference, and every inference carries uncertainty. The PETM is not proof of a prior civilization. Frank and Schmidt were extremely clear about that. They explicitly stated in their paper that they considered the prior civilization hypothesis unlikely. But the PETM is a demonstration that events which would be consistent with industrial activity can occur from entirely natural causes, which means that the inverse is also true. Events caused by industrial activity could, in principle, look entirely natural. That symmetry, the fact that the record can look the same from either cause, is the Silurian hypothesis in its most precise form, not a claim, not evidence, an epistemological boundary, a marked edge on the map of what we can know. And on the other side of that edge, there is something even stranger waiting, a chapter of human history that came closer to being erased entirely than we usually allow ourselves to think about. Part 7. 12,008. 100 years ago, the sudden reset. Everything we have discussed so far lives in geological time, millions of years, timescales so long they're almost abstract. Now, we come to something different, something that happened not millions of years ago but roughly 12,800 years ago, a period that, in historical terms, is almost recent, close enough that the people alive when it happened were anatomically identical to us. They had the same brains, the same language capacity, the same basic cultural toolkit. They were us, wearing different clothes in a different world, and something hit that world with a force that almost reset it entirely. The period is called the Younger Dryas, named after a small flowering plant, Dryas octopetala, whose pollen appears suddenly and abundantly in sediment cores from this period across the northern hemisphere, an indicator plant of cold, open, tundra-like environments. The Younger Dryas was a period of abrupt, dramatic cooling that interrupted what should have been the steady warming trend after the last glacial maximum. Instead of continuing to warm, the northern hemisphere's climate suddenly lurched back toward near-glacial conditions for roughly 1,200 years. The temperature changes were not subtle. Ice core records from Greenland show that temperatures in that region dropped by somewhere between 10 and 15 degrees Celsius within what appears, at the resolution of ice core dating, to have been a matter of decades, possibly faster. The resolution of ice core data from this period, roughly 12,800 years ago, makes it genuinely difficult to distinguish between a change that happened over decades and one that happened over a few centuries, but either way, on any human scale, this was catastrophic. Ecosystems that had been adapting to warming conditions for thousands of years suddenly found themselves in a climate they had not evolved for. Agricultural patterns that proto-agricultural communities had been developing were disrupted. Megafauna, the large animals that had survived the last glacial maximum, collapsed in enormous numbers across multiple continents during or near this period. The Clovis culture, the earliest well-documented human culture in North America, disappears from the archaeological record at this time. Not just declines, disappears. The characteristic Clovis stone tool tradition, which had spread across North America, vanishes within what appears to be a very short period. Whether the people died, migrated, or simply changed their material culture rapidly enough that their successors are not recognizable as Clovis descendants is still debated. But the archaeological discontinuity is real and sharp. What makes the Younger Dryas directly relevant to the question we're asking is not just the event itself, but what the event demonstrates about the geological record and about civilization. The Younger Dryas was a civilization-scale disruption, not of an industrial civilization, but of the nascent human cultures that were beginning to develop the social and agricultural foundations that would eventually produce civilization. Whatever those groups were building, whatever knowledge they were accumulating, whatever social structures they were developing, all of it was stress-tested by a climate catastrophe that lasted 1,200 years. And the record of that period is, in crucial ways, incomplete. Not because we haven't looked, because the event itself erased or disrupted much of what came before it. This is the key connection to our central thread. Even when we are in the period of actual human history, the period where our own species was alive and active, sudden catastrophic events can erase chapters from the record. They can disrupt the developmental trajectory of cultures, causing them to appear, disappear, and reappear in forms that look discontinuous. They can bury or destroy physical evidence. They can break chains of cultural transmission that might otherwise have preserved knowledge through oral tradition. The Younger Dryas shows us that even in the relatively recent past, events of sufficient magnitude can produce exactly the kind of gap in the record that makes before and after look like two entirely different stories. And that question of what actually caused the Younger Dryas, what fired that trigger at 12,800 years ago, is one of the most contested debates in the entire field of quaternary science. Part 8. Evidence that something hit us. For most of the 20th century, the leading explanation for the Younger Dryas onset was a disruption of ocean circulation caused by the sudden drainage of massive glacial lakes into the North Atlantic. During the last glacial maximum, enormous quantities of meltwater were held in enormous ice-dammed lakes in North America, Lake Agassiz being the largest, a body of water bigger than any current freshwater lake on Earth. The hypothesis was that at roughly 12,800 years ago, the ice dam holding this water gave way, releasing an enormous pulse of cold freshwater into the North Atlantic in a very short period. Cold freshwater is less dense than cold salt water, so instead of sinking and driving thermohaline circulation, it floated, essentially putting a lid on the North Atlantic conveyor belt and shutting down the heat transport mechanism that keeps Western Europe and the northeastern United States relatively warm. This meltwater pulse hypothesis is physically plausible and supported by some geological evidence of lake drainage events around this period. It remains an important part of the scientific discussion, but a significant body of research published over the last 2 decades has complicated the picture considerably, and the complications involve a type of evidence that was not widely anticipated when the meltwater hypothesis was first proposed. Starting in the early 2000s and accelerating through subsequent years, a group of researchers began reporting the presence of a distinctive set of materials in sediment and soil layers corresponding to roughly 12,800 years ago. The materials were found at sites spread across 4 continents: North America, Europe, the Middle East, and potentially South America, in a pattern suggesting a simultaneous global depositional event. The specific materials included microscopic diamonds, particularly in a form called nanodiamonds, that require extremely high pressures and temperatures to form naturally. They included tiny spheres of glass formed at temperatures above 2000 degrees Celsius, temperatures that don't occur in any natural geological process operating at the surface. They included microspherules of iron and silicon that are structurally similar to materials found at confirmed impact sites and to materials produced during nuclear tests. Together, these proxies form what researchers call a biomass burning signature combined with an impact signature, evidence of an event that produced simultaneously very high temperatures and very high pressures across an enormous geographic area. The researchers who first compiled this evidence proposed that it was consistent with the airburst or surface impact of a fragmented comet, a swarm of comet fragments, potentially from the torrid meteor stream, striking or exploding over multiple continents simultaneously at approximately 12,800 years ago. The Younger Dryas impact hypothesis, as it came to be known, generated enormous controversy. It was challenged, replicated by some teams and failed to replicate by others, debated at conferences, and subjected to intense methodological scrutiny. Some of the controversy was legitimate scientific skepticism about whether the specific markers claimed were truly anomalous or were within the range of natural variation. Some of it was, arguably, a scientific community struggling to integrate an uncomfortable idea into a well-established framework. Then, in 2025, a development occurred that may prove significant in resolving at least one corner of this debate. Researchers reported the discovery of what they described as the first candidate physical site for a Younger Dryas impact in Louisiana, a depression in the geological record associated with the right time period, containing the right assemblage of shocked materials, melted glass, and anomalous geochemical signatures. The site contains materials that share characteristics with those found at nuclear test sites, specifically the kind of glass produced when a high-temperature event fuses surface sediments in a way that requires temperatures far exceeding anything a conventional wildfire or volcanic activity produces at the surface. The Louisiana site is still under active investigation and has not reached consensus confirmation in the scientific community. But it represents something significant: the first geophysical candidate for a ground truth location associated with the Younger Dryas impact hypothesis. Previously, the hypothesis rested almost entirely on the distribution of microscopic materials across sites, real evidence, but dispersed and indirect. A physical depression with locally concentrated evidence of extreme temperature events provides a different kind of data point, one that can be studied, dated, and characterized with high-precision methods. The multi-impact hypothesis that accompanies this work is particularly striking for our purposes tonight. If the Younger Dryas onset was caused not by a single large impactor, but by a swarm of fragments from a disintegrating comet body, a scenario that is physically well understood and actually considered the more likely mode of impact for large comet-derived objects, then you would expect the evidence to be geographically distributed. You would expect impact signatures on multiple continents, in multiple ocean basins, over a relatively short period of time, and that is, roughly speaking, what the evidence pattern looks like, though the interpretation of that pattern remains genuinely contested. What this means for the historical record, and here is where the connection to our central question bites hard, is that a cosmic impact of sufficient scale can accomplish in hours what geology normally takes millions of years to do. It can erase physical structures over enormous areas. It can trigger wildfires that destroy organic evidence. It can cause climate disruptions that collapse agricultural systems and force population movements, breaking chains of cultural transmission. It can deposit a layer of impact-associated materials on top of whatever was there before, burying it under a new event signature. And it can do all of this without leaving, in the geological record millions of years later, any marker that says this was caused by something other than a natural event. Part 9. Competing Explanations. The honest state of the science around the Younger Dryas onset is that we have two families of hypotheses, the meltwater pulse family and the cosmic impact family, that may both be partially right and are not necessarily mutually exclusive. A fragmentary comet impact could have triggered or accelerated the meltwater pulses that disrupted North Atlantic circulation, or the meltwater pulses could have been the primary driver, with the impact proxies representing a real but climatically secondary event. Or the impact hypothesis is overstated, and the unusual materials can be explained by volcanic activity, wildfires, or other non-impact mechanisms. This is not scientific failure. This is science working exactly as it is supposed to work, with competing hypotheses tested against evidence, debates conducted through peer review, and conclusions held provisionally until the evidence becomes clear enough to resolve them. The fact that serious researchers are still debating the cause of the Younger Dryas onset 40 years after it was first clearly described is not a sign that something has gone wrong. It's a sign that the question is genuinely difficult. But for our purposes tonight, the Younger Dryas debate illustrates something important about the nature of the geological record. Even for an event that occurred only 12,800 years ago, an event within the era of anatomically modern humans, an event that left widespread multi-continental evidence, the causal question is unresolved. We can see clearly what happened. We cannot yet say with certainty what caused it. Now scale that uncertainty backward. Think about trying to determine the cause of an event from 56 million years ago, or from 100 million years ago, with a record that has been subjected to 56 million years of additional geological processing since the event occurred. The PETM is actually better studied than many geological events because of its geological recency relative to most of Earth's history, and because of its relevance to modern climate science. But the trigger question for the PETM, exactly what fired the gun, is even less resolved than the trigger question for the Younger Dryas. This is the compounding uncertainty at the core of what we're exploring. Each step backward in time makes the causal question more difficult, the evidence sparser, and the interpretation more dependent on assumptions. And at some point, the Silurian hypothesis tells us exactly where. The record becomes ambiguous enough that we genuinely cannot say with confidence whether an unusual event has a natural or anthropogenic cause. But something appears in the geological record that, unlike anything else we've discussed, cannot be attributed to geological processes at all. It was built by hands, it was constructed with intention, and it appears at exactly the moment in human history when, according to our best understanding of how civilizations develop, it should not have been possible. Part 10. Göbekli Tepe, the temple before civilization. About 15 kilometers northeast of the city of Şanlıurfa in southeastern Turkey, on a ridge overlooking what was once a fertile valley, sits a site that has been quietly rewriting our understanding of human prehistory since its excavation began in earnest in 1994. The site is called Göbekli Tepe, which translates roughly from Turkish as Potbelly Hill. The name is not majestic. The implications of what lies beneath that hill are. Göbekli Tepe dates to approximately 9,600 BCE, roughly 11,500 years ago. This dating has been independently confirmed multiple times using multiple methods, including radiocarbon dating of organic material from the site and the stratigraphy of the surrounding sediments. It is not in dispute. What is in dispute, or rather, what remains deeply puzzling, is everything else about it. The site consists of multiple circular or oval enclosures, each containing T-shaped stone pillars arranged in specific patterns. The pillars are carved from local limestone, and they range in height from approximately 3 meters to over 5.5 meters, roughly 18 feet, and in weight from roughly 10 tons to estimates as high as 20 tons for the largest examples. The surfaces of many pillars are covered with elaborate relief carvings, animals, abstract symbols, geometric forms, foxes, boars, birds, scorpions, spiders, and other creatures are depicted with a precision and artistic consistency that implies not just individual craftsmanship but a shared symbolic tradition. These are not doodles, they are not random. The same animals appear across multiple pillars in multiple enclosures, executed with the same stylistic conventions, a vocabulary of imagery that implies a school of thought, a cultural agreement about what symbols meant and how they should be rendered. Some of the pillars appear to be anthropomorphic, meaning they may represent human or human-like figures. Certain examples have what appear to be arms carved along their sides, hands meeting at the front of the pillar, and belts or garments suggested by carved details near what would be a waist. If these are indeed stylized human figures, then Göbekli Tepe is not just a construction achievement. It is a symbolic world, a place where the people who built it were encoding something about how they understood themselves in relation to the animals, the sky, and whatever forces they believed governed their existence. Here is what makes Göbekli Tepe genuinely anomalous within the archaeological record of human development. The site predates agriculture, it predates pottery, it predates any kind of permanent settlement that we can identify in the archaeological record of the region. According to the conventional model of how civilizations develop, complex monumental architecture is a product of agricultural surplus. You can only build enormous structures when you have a social system complex enough to free some members of the community from food production full-time, which requires sufficient agricultural output to support non-farmers. Agriculture in this region of the world doesn't appear in the record until roughly 10,500 BCE, approximately 900 to 1500 years after the earliest layers of Göbekli Tepe. Let that sink in for a moment, because it genuinely inverts the sequence we thought we understood. The standard story of human development runs like this. People learn to farm, farming creates surplus, surplus allows specialization, specialization allows some people to become builders and priests and administrators instead of farmers, and that social complexity eventually produces things like temples and monuments. Göbekli Tepe appears to run that sequence backward. The temple comes first, the farming comes later, which either means our model was wrong, or something about the people who built Göbekli Tepe doesn't fit the model, and either way, we have some rethinking to do. The builders of Göbekli Tepe were, by the conventional archaeological characterization, hunter-gatherers. Mobile or semi-mobile groups who moved with animal migrations and seasonal plant availability lived in temporary structures and had not yet developed the social stratification, labour specialisation, and resource surpluses associated with complex societies. And yet they quarried enormous limestone blocks from the bedrock, transported them to a hilltop, and erected them with a precision of placement and a consistency of artistic tradition that implies organised, coordinated labour, possibly over extended periods, possibly involving significant numbers of people, certainly involving some form of planning, leadership, and cultural continuity. The quarry areas are still visible near the site. Unfinished pillars remain partially attached to the parent rock, giving us a direct window into the production process. One unfinished pillar still in the quarry measures approximately 7 meters in length and would have weighed an estimated 50 tons, larger than anything successfully erected at the site, which may explain why it was abandoned. But its presence tells us something important. The people working here were thinking big. They were not tentatively chipping away at small stones to see what happened. They were attempting to extract and move objects of genuinely enormous scale, and in most cases they succeeded. Moving a 20-ton limestone pillar across several hundred meters of uneven terrain, up a slope, and setting it precisely into a prepared socket carved into the bedrock floor of an enclosure, without wheeled vehicles, without metal tools, without draft animals in any confirmed capacity, is a serious engineering problem, not an impossible one, but a serious one. It requires either mechanical ingenuity, levers, sledges, ropes, prepared trackways, or a very large, very coordinated labour force, or both. And coordinating a large labour force requires feeding them, which brings us back to the agricultural question. How do you feed the workers building a monument that predates agriculture? Some researchers have proposed that the construction activity itself created the pressure to develop more reliable food production, that Göbekli Tepe didn't follow civilization, it helped create it. The monument built the farmer rather than the farmer building the monument. The site was also, at some point around 8000 BCE, deliberately buried. The enclosures were filled in, not naturally silted up, but intentionally backfilled with sediment, rubble and debris, covering the pillars and preserving them beneath a mantle that remained in place until the 1960s, when a survey mission from the University of Istanbul noted the site and misidentified it as a medieval cemetery. It took until Klaus Schmidt's excavation, beginning in 1994 and continuing until his death in 2014, to reveal what was actually there. Schmidt dedicated 2 decades of his professional life to this site and described it, in his own words, as the world's oldest temple. He was not given to overstatement. Why was it buried? Nobody knows. There are hypotheses: ritual closure of sacred spaces, protection from some anticipated event, abandonment following a cultural shift, but the evidence doesn't resolve the question. What we do know is that the burial was not hasty or careless. The fill material was deposited in a way that preserved the pillars rather than toppling them. Whoever did it knew what they were covering and chose to cover it anyway, carefully. That decision, to bury something enormous, elaborate, and clearly significant rather than maintain or build upon it, is one of the strangest things about an already very strange site. It implies a relationship with the structure that we don't have the cultural context to understand. They built it over centuries, used it for some purpose we can only speculate about, and then put it to bed under meters of fill as if closing a chapter. The intentional burial is one of the site's most tantalizing features, because it means we're almost certainly looking at a fraction of what was once there. The buried portions are, paradoxically, the best preserved, while the portions that remained exposed have been affected by millennia of weathering and agricultural activity. Geophysical surveys using ground-penetrating radar have revealed additional enclosures still fully buried beneath the surface, perhaps 16 or more in total, of which only a handful have been excavated. The site we have seen is the visible tip of something much larger, and given that excavation has been proceeding for 30 years and is still nowhere near complete, we may be a generation away from understanding the full scale of what is here. Now here is where Göbekli Tepe connects back to the question we have been building all evening, the question about what the record can actually tell us and what it quietly conceals. The site appears in the archaeological record without a clear developmental sequence leading up to it. There is no series of smaller, simpler versions that shows Göbekli Tepe being developed gradually from more primitive precursors in this region. It appears at an extraordinary level of scale and sophistication, and the conventional explanation that hunter-gatherers were capable of more complex social organization than we previously assumed is probably correct. But probably correct is doing a lot of work in that sentence. It requires revising our previous model substantially, acknowledging that complexity can emerge in forms and sequences we did not predict, and sitting with the uncomfortable fact that the steps leading to Göbekli Tepe are not preserved in any record we currently have access to. And that is exactly the pattern the Silurian hypothesis predicted we would find. Not necessarily evidence of something impossible, but evidence of gaps. Gaps where the record goes quiet right before something remarkable appears. Gaps that could mean nothing, or could mean that the developmental history of human complexity is longer, stranger, and less linear than the textbooks currently suggest. Göbekli Tepe does not prove a prior civilization, but it proves, beyond any reasonable doubt, that what we know about our own past is incomplete in ways that matter, and that the next discovery, whenever and wherever it comes, has a genuine chance of changing the story again. Part 11. Knowledge without a source. The engineering challenges presented by Göbekli Tepe's construction were not trivial, and I want to spend a moment actually walking through what those challenges involved, because the numbers matter here, and they don't get discussed enough in casual treatments of the site. The T-shaped pillars were quarried from the limestone bedrock of the surrounding plateau. You can still see unfinished pillars in the quarry areas, some still partially attached to the parent rock, frozen mid-extraction like a project someone walked away from and never came back to. Quarrying limestone pillars weighing up to 20 tons using stone tools, flint chisels, harder stone hammers, wooden wedges driven into natural fracture lines is genuinely difficult. Not impossible, but the kind of difficult that requires accumulated practical knowledge passed down through generations, refined through repeated trial and error, and applied with patience measured in years rather than weeks. Transporting those pillars from the quarry to the construction site involved moving objects the weight of 4 adult African elephants across several hundred meters of uneven sloping terrain. Some of the distance is relatively flat. Some of it involves significant elevation changes. There are no confirmed traces of prepared roads, wooden trackways, or other purpose-built infrastructure for the transport, though absence of evidence in 11,000-year-old terrain is not strong evidence of absence. The most commonly proposed mechanisms involve wooden sledges, ropes woven from plant fibre, lubricated surfaces, and large numbers of people pulling in coordination. Experimental archaeology, the practice of actually trying to replicate ancient construction techniques using period-appropriate tools and methods, has demonstrated that these approaches work. They are slow, they require organisation, and they require more people than a small band of 20 or 30 hunter-gatherers could provide, but they work. Erecting the pillars once transported is its own separate engineering problem. The pillars don't just stand on the surface, they are set into sockets, carved precisely into the bedrock floor of each enclosure, sized to receive the specific pillar that goes into them. The socket has to be deep enough and shaped correctly to hold the pillar vertical and stable against its own considerable weight and the lateral forces of wind. Getting a 20-ton pillar from horizontal on the ground to vertical in a prepared socket, without it toppling during the process and killing everyone involved, requires a lifting and guiding system of some sophistication, probably involving earthen ramps, wooden frames, ropes, and a great deal of very careful coordination. One mistake at the wrong moment and you lose the pillar, the socket, and possibly several people. The fact that they did this repeatedly, across multiple enclosures, over what appears to have been centuries of construction activity, suggests a tradition of accumulated technical knowledge that was taught, refined, and transmitted across generations. None of this is impossible. It is important to say that clearly and mean it. It's the kind of thing that large groups of motivated people with accumulated practical knowledge can accomplish. And we know that because Göbekli Tepe is not the only example of prehistoric monumental construction. Stonehenge demonstrates it. The megalithic temples of Malta demonstrate it. The stone circles of the British Isles, the dolmens of Western Europe, the Moai of Easter Island. All of these show us that prehistoric people were capable of remarkable, sustained, large-scale engineering feats, using nothing more than stone tools, organic materials, and organised human effort. But the difference at Göbekli Tepe is the date, and the date is everything. Stonehenge began around 3000 BCE, roughly 5,000 years after the earliest layers of Göbekli Tepe. The megalithic temples of Malta date to around 3800 BCE. The stone circles of the British Isles are similarly positioned in the mid to late Neolithic, by which point agriculture had been established in those regions for thousands of years, and the social surpluses it created were well documented. Göbekli Tepe predates all of them by several thousand years, and does so in a period when, according to our previous understanding, the social complexity required for such a project simply should not have existed yet. It's a bit like finding a functioning steam engine in a museum collection dated to the 12th century. The object is real, the date is confirmed, and your model of how technology develops just became significantly more complicated. The astronomical interpretation of Göbekli Tepe has added another layer entirely to an already complicated picture. A 2024 study by Martin Sweatman proposed that certain carved symbols on the pillars represent astronomical events, specifically that a particular arrangement of symbols on what is called the vulture stone, one of the most elaborately carved pillars at the site, encodes a date corresponding to approximately 10,800 BCE and depicts a comet impact event consistent with the onset of the Younger Dryas cooling period we discussed earlier. If Sweatman's reading is correct, the people who built Göbekli Tepe were not just engineers and artists. They were astronomers, carefully tracking the movements of stars and encoding celestial events in stone with sufficient precision to be readable 11,000 years later. This interpretation is controversial, and that is worth being precise about. Many archaeologists and astronomers have raised significant and substantive objections to the methodology used to align the carvings with specific astronomical configurations. The process of matching animal symbols to star patterns involves interpretive choices at several steps, and different choices produce different results. The criticism is legitimate, and the debate is ongoing. But here is what I find significant about that debate. The hypothesis is being actively discussed in peer-reviewed literature rather than simply dismissed. Researchers are engaging with it seriously enough to publish detailed rebuttals, which means they consider it worth rebutting, and that level of engagement, whatever the ultimate conclusion, tells you something about the genuine complexity of what is carved on those pillars. These are not simple scratches. They are a symbolic system sophisticated enough that trained researchers in the 21st century are still arguing about what it means. What's particularly interesting about the agricultural question, and this is the part that genuinely inverts the story we thought we knew, is its directionality. The conventional assumption, the one that sat unchallenged in archaeology textbooks for most of the 20th century, was that agriculture creates the surplus that enables monumental architecture. You farm, you eat reliably, some people are freed from farming, those people build things. That's the sequence. Göbekli Tepe appears to run it backward, and the more researchers have studied the surrounding region, the more evidence has accumulated that agriculture in the Fertile Crescent emerged in the same general area and time period as Göbekli Tepe's construction, possibly as a consequence of it, rather than a precondition for it. The reasoning goes like this. Building and maintaining Göbekli Tepe required feeding large numbers of people engaged in physically demanding labour over extended periods, years, decades, possibly centuries of intermittent but recurring construction and ceremonial activity. Wild game hunting and plant gathering, even in a relatively productive environment, is a variable and uncertain food source. If you need to guarantee that 100 or 200 workers can be fed reliably enough to show up and move 20-ton stones, you have a very strong incentive to develop more controlled, predictable food production. The monument creates the agricultural pressure. The monument builds the farmer, rather than the farmer building the monument. It's an elegant hypothesis, and the geographical and temporal overlap between early Göbekli Tepe construction and the earliest evidence of serial domestication in the same region is suggestive, though not yet conclusive. This is a genuinely interesting archaeological hypothesis, and it doesn't require any lost civilization or supernatural intervention to make sense of. It just requires acknowledging that our previous model of human development, forager to farmer to complex society to monumental architecture, neatly sequenced and causally obvious, was oversimplified in ways that a single excavation on a hilltop in Turkey has now made impossible to ignore. The development of human complexity was messier, more varied, more surprising, and probably more regionally specific than the broad strokes narrative we'd been telling. Different populations found different paths. Some of those paths don't look like what we expected, and we're only beginning to understand why. And if that is true for a period we can still investigate archaeologically, a period 11,000 years ago that left physical structures, organic material for radiocarbon dating, and carved images we can analyse with modern imaging technology, then it raises an obvious and somewhat vertiginous question about periods of human prehistory that are far more deeply buried. What did the 50,000 years before Göbekli Tepe look like? We have stone tools, some cave art, scattered skeletal remains. We do not have anything like the resolution we have for the Neolithic, and the geological processes we discussed at the beginning of tonight have been working on that record for 50 millennia longer than they have been working on Göbekli Tepe. The connection back to our central thread is this. Göbekli Tepe represents a case where advanced, organised, symbolically sophisticated human behaviour appears in the archaeological record without a clear preceding developmental sequence visible to us. The record before it does not show us the steps that led to it. Whether those steps existed and are simply unpreserved, buried, eroded, submerged under 120 metres of post-glacial ocean, or whether Göbekli Tepe genuinely represents a discontinuity, a leap that our current evidence cannot explain, is a question the record does not yet answer. And that kind of gap, between what we know existed and what we would expect to see leading up to it, is exactly the kind of gap that everything we have covered tonight predicts we should find, even in the recent past, even when we are looking carefully, even when the site is right there, visible on a hilltop waiting to be found. Part 12. Echoes in Stone. There is one more anomaly worth addressing before we pull back to the full picture, and I want to be precise about how I'm framing it, because this one gets misrepresented constantly, in both directions, and it deserves a careful treatment. The Great Sphinx of Giza is one of the most studied monuments on Earth. It has been measured, photographed, scanned with ground-penetrating radar, analysed with seismic equipment, and written about in more academic papers than most people will read in a lifetime. Its conventional date, around 2500 BCE, during the reign of Pharaoh Khafre of the 4th dynasty, is supported by significant archaeological and historical evidence. The proximity of the Sphinx to Khafre's pyramid and causeway, the dream stele of Thutmose IV, which associates the Sphinx with royal lineage, the stylistic similarities between the Sphinx's face and known representations of Khafre, and the broader archaeological context of the Giza Plateau during the Old Kingdom period, all of this forms a coherent and mutually reinforcing body of evidence. That dating is not in serious dispute within mainstream Egyptology, and I am not going to pretend otherwise. But there is a specific, technical, geological argument about the Sphinx that has been sitting in the academic literature since 1991, that has not been resolved, and that deserves to be understood on its own terms rather than dismissed because of the company it sometimes keeps in popular media. The argument was developed primarily by Robert Schoch, a geologist and associate professor at Boston University, not an archaeologist, not a historian, but a geologist, which turns out to matter for the specific claim he is making. Schoch's specialty is the weathering and erosion of rock formations, and it was through that lens that he first examined the Sphinx enclosure in the early 1990s at the invitation of researcher John Anthony West. What Schoch observed, and what he has documented extensively in published work, including peer-reviewed geological literature, is that the erosion patterns visible on the body of the Sphinx, and more importantly on the walls of the enclosure carved into the bedrock around it, do not look like what you would expect from wind and sand erosion. Wind erosion operating on limestone over thousands of years tends to produce a characteristic pattern: horizontal layering, undercutting of softer rock strata, relatively sharp boundaries between eroded and uneroded zones, and a surface texture shaped by the predominantly horizontal movement of abrasive particles. What shock found on the Sphinx enclosure walls was different. The erosion profiles are rounded and undulating in a vertical direction. The channels run top to bottom rather than horizontally. The overall morphology, in Schoch's geological assessment, is characteristic of water precipitation erosion, the kind produced when significant rainfall falls on exposed rock over an extended period, runs down the vertical face, infiltrates fractures and softer layers, and gradually rounds and deepens the surface through a combination of hydraulic action and chemical dissolution. The distinction between these two erosion types is not trivial or subjective in geological terms. They produce measurably different profiles that trained geologists can distinguish with reasonable confidence when examining fresh examples in the field. Schoch's argument is not that he prefers one interpretation aesthetically. It is that the physical profile of the erosion on the Sphinx enclosure walls is most consistent, in his geological judgment, with prolonged water precipitation erosion rather than wind and sand erosion. If Schoch is correct about the mechanism, the implication for dating is significant and direct. The Giza Plateau today receives very little rainfall. The region is hyper-arid, with annual precipitation measured in millimeters rather than centimeters. For water precipitation erosion to have produced the profiles Schoch describes, the Sphinx enclosure would need to have been exposed to sustained, significant rainfall over an extended period. And the paleoclimatic record for the Giza region is actually quite well established on this point. The area experienced substantially higher rainfall during the period known as the African Humid Period, sometimes called the Green Sahara, which occurred roughly between 11,000 and 5,000 years ago. During this period, the Sahara was not a desert. It was a region of savannas, lakes, and river systems, supporting human populations and wildlife across an area that is today completely uninhabitable. Rainfall was regular and significant. After approximately 5000 BCE, the African Humid Period ended as orbital cycles shifted Earth's climate. The monsoon rains retreated southward, and the Sahara dried out over a period of centuries to millennia into roughly its current configuration. If the erosion on the Sphinx was produced by rainfall, and if that rainfall corresponds to the African Humid Period, then the erosion, and by extension the monument itself, which had to exist before it could be eroded, predates 5000 BCE by some margin. Schoch has been cautious about exactly how far back he pushes the date, suggesting the monument's origins could lie somewhere between 7000 and 10,000 BCE, possibly earlier. This would place the original construction of the Sphinx, or at least of the body, which is carved directly from the bedrock, in the same general time period as Göbekli Tepe, and would imply a level of monumental construction capability in the Nile Valley region during the early Holocene that the conventional archaeological record does not currently support. The mainstream Egyptological and geological response to Schoch's hypothesis has been substantive and worth taking seriously, because the counter-arguments are not simply dismissive. Mainstream researchers have pointed to several alternative explanations for the erosion profiles. First, the Giza region does experience occasional intense rainfall events even in its current hyper-arid state, rare but real and capable of producing significant runoff and erosion in short periods. Second, the subsurface geology of the Giza Plateau involves water-bearing strata, and moisture can migrate through rock and emerge on exposed faces through a process called seepage, which can produce erosion profiles that superficially resemble precipitation erosion. Third, the limestone of the Sphinx body and enclosure walls is heterogeneous. It varies in hardness and composition across different layers, and differential weathering of these layers by a combination of mechanisms could produce the rounded profiles Schoch attributes to rainfall. The debate has not been resolved to the satisfaction of either camp, and that resolution is unlikely to come without a more systematic, high-resolution geological survey of the enclosure walls using modern quantitative methods, detailed surface mapping, mineralogical analysis of the weathered zones, isotopic analysis of secondary minerals deposited in fractures, and comparison with erosion profiles from other known precipitation-eroded limestone formations in the region. Some of this work has been done in preliminary form. None of it has been comprehensive enough to definitively close the argument. There is one additional detail about the Sphinx that gets raised in this context and deserves a brief mention: the disproportionate relationship between the monument's head and its body. The Sphinx's body is enormous, roughly 73 metres long and 20 metres tall at the shoulder. The head, by comparison, is relatively small and shows significantly less erosion and weathering than the body. Some researchers, including Schoch, have suggested that the head was recarved at a later date, that the original monument had a different head, possibly an animal head consistent with the lion-like body, and that it was later reshaped into the human face we see today, which is conventionally identified as Khafra. The recarving hypothesis would explain the disproportionate size. Recarving reduces the head, and the differential weathering. A recarved surface is fresher and therefore less eroded. This interpretation is speculative and contested, but it is not physically implausible, and it is the kind of detail that, if true, would mean the Sphinx we are looking at today is a palimpsest, an older monument rewritten by a later culture, the original form preserved underneath but no longer visible on the surface. What the Sphinx erosion debate represents for our purposes tonight is not proof of an older civilization or a rewritten history. It is something more specific and more useful than that. It is a demonstration that even for a monument we can physically visit, photograph from every angle, scan with ground-penetrating radar, and contextualize with thousands of years of written historical records, even for that monument, experts genuinely disagree about what the physical evidence means. The geological interpretation of erosion profiles on one of the world's most famous structures is, after more than 30 years of debate, unresolved. The evidence does not speak for itself with the clarity we would like. Specialists in different fields, geology on one side, Egyptology on the other, look at the same object and reach different conclusions based on the methodologies and interpretive frameworks their disciplines provide. If that is true for the Sphinx, sitting in open desert, accessible to researchers from around the world, surrounded by one of the richest bodies of historical and archaeological context in existence, then consider what it implies for structures and events far older, far less preserved, and far more thoroughly processed by the geological mechanisms we have been describing all evening. The ambiguity is not an exception. It is not a failure of the scientific method. It is what the record looks like when you look at it honestly. The monuments that survive are a small, skewed, geographically biased sample of what was once there. They have survived precisely because they are large and stone and relatively recent. The rest, everything smaller, everything older, everything built on coastlines that are now ocean floor, has been erased by exactly the mechanisms we have been describing all evening, and the Sphinx, contested and ambiguous even in its visibility, is perhaps the most honest reminder of what we are actually working with when we claim to know what happened in the past. Part 13. The flood that everyone remembers. There is a category of evidence that sits entirely outside the geological record, that cannot be carbon dated or isotopically analysed, that leaves no chemical signature in sediment cores and no physical trace in rock layers, and that has nonetheless persisted through more than 10,000 years of human history across every inhabited region of the planet. It is the category of cultural memory, specifically the memory of a catastrophic flood. And before you file that under mythology and move on, I want to ask you to hold off on that instinct for a few minutes, because the distribution and structure of these stories is genuinely strange in ways that deserve careful attention. Flood myths are not a coincidence of cultural evolution or a universal psychological archetype, though they may incorporate those elements. They are not simply the product of human anxiety about water, or the inevitable product of any culture living near a river. They are distributed globally with a specificity and structural consistency that is difficult to explain if they are purely invented, if each culture simply made up a flood story independently, with no shared historical referent. The specific narrative architecture of these myths, not just the general idea of a flood, but the particular sequence of events, the warning, the vessel, the survival, the aftermath, recurs across cultures so geographically separated that independent invention of the same detailed structure strains probability, there are more than 500 distinct flood narratives identified by anthropologists across human cultures on every inhabited continent except Antarctica. 500. That is not a handful of coincidences. The specific structure of these myths varies enormously in local detail. The identity of the warning deity, the nature of the vessel, the reason for the flood, the identity of the survivor. But the underlying architecture occurs with a consistency that implies these stories are drawing on a shared historical experience. An experience that was transmitted orally across countless generations, distorted and elaborated and personified by the cultural context through which it passed, but preserving at its core a memory of something that actually happened. The Epic of Gilgamesh from ancient Mesopotamia is the oldest written example we have. The tablets on which it is written date to around 2100 BCE, but the story they record is substantially older. The oral tradition from which it was drawn predates the writing by an unknown period, possibly by thousands of years. The flood narrative within the Epic of Gilgamesh is so structurally similar to the biblical account of Noah. The divine warning to a specific individual, the construction of a large vessel, the loading of animals, the flood that destroys all other life, the survival of the chosen group, the eventual grounding of the vessel on a mountain, the release of birds to test whether dry land has appeared, that when the Gilgamesh tablets were first translated by George Smith in 1872, the recognition was immediate and caused a public sensation. These were not two cultures independently inventing similar stories. They were drawing on a shared tradition whose origins predate both the Sumerian and Hebrew written records. The structural similarities extend much further than the Mesopotamian and biblical traditions. The Atrahasis myth, another Mesopotamian account predating even the Gilgamesh version in some of its elements, follows the same basic architecture. Hindu mythology preserves the story of Manu, a righteous man warned by a fish, eventually revealed as an avatar of the god Vishnu, to build a large boat and load it with the seeds of all living things to survive a coming deluge that will destroy the world. The fish guides the boat to safety on a northern mountain as the waters rise. The structural parallel to Noah and Utnapishtim, Gilgamesh's flood survivor, is unmistakable. Greek mythology has the story of Deucalion, son of Prometheus, who was warned of a flood sent by Zeus to destroy humanity, built a chest in which he and his wife Pyrrha survived, and landed on Mount Parnassus or Mount Othrys, depending on the version, when the waters receded. Deucalion then repopulated the earth, just as Noah does in the biblical account. Move further afield and the pattern continues. The Okanagan people of the Pacific Northwest preserve a flood narrative. The Ojibwe of the Great Lakes region have one. The Muisca of Colombia, the Inca traditions of the Andes, various Mesoamerican cultures. Flood narratives appear across the Americas with a frequency and structural consistency that early European missionaries frequently noted with bewilderment, having expected to find these stories only in cultures with access to the biblical tradition. In China, the story of Gun Yu and the Great Flood is one of the foundational myths of Chinese civilization, describing a catastrophic inundation that lasted for generations and was only controlled through the engineering efforts of the hero Yu, who went on to found the Xia dynasty. In Mesopotamia, in India, in Greece, in the Americas, in China, the flood is everywhere, and it is always catastrophic, always world-ending within the narrative frame, always survived by a specific individual or group who preserve life and begin again. The Aboriginal Australian examples deserve particular attention because they provide something the others cannot: independent geological verification. Certain Aboriginal Australian oral traditions from coastal communities describe specific geographical features, bays, islands, reef formations, that were once dry land, and describe the flooding of that land by a rising sea within the narrative memory of the culture. Researchers comparing these narratives to the known sea level rise history of the Australian coastline have found cases where the geographical details of the oral tradition correspond accurately to the actual topography of the now submerged coastal landscape, dated by geological methods to between 7,000 and 10,000 years ago. This is not a small thing. This is an oral tradition accurately preserving specific geographical information about a landscape that has been underwater for 7 to 10,000 years. The information was not written down. It was not carved in stone. It was transmitted person to person, generation to generation, through song and ceremony and the structured oral practices that traditional cultures developed precisely for the purpose of preserving important information accurately across time. And it worked. The geography is right. The timing is consistent. The tradition preserved what the geological record confirms happened. This gives us a calibration point for thinking about oral tradition as a form of archive. If Aboriginal Australian oral traditions can accurately preserve geographical memory across 10,000 years of transmission, then the structural consistency of flood narratives across 500 cultures worldwide starts to look less like coincidence and more like signal. Not proof. Oral traditions distort, mythologize, and personify the events they preserve, but signal. Evidence that something real is being remembered, even if the remembering has transformed it in ways that make the original event difficult to extract cleanly. The geological context for what that real event was is actually not mysterious at all. Between approximately 19,000 and 7,000 years ago, global sea levels rose by approximately 120 meters as the ice sheets of the last glacial maximum melted. 120 meters is the height of a 40-story building. That rise didn't happen smoothly or gradually in human experiential terms. It included several episodes of dramatically accelerated rise called meltwater pulses, during which enormous quantities of meltwater from collapsing ice sheets entered the ocean in geologically very short periods. Meltwater pulse 1A, occurring around 14,600 years ago, may have raised global sea levels by somewhere between 10 and 15 meters over a period as short as a few centuries. For a coastal community living on low-lying ground near the shore, the kind of ground where fertile soil, fresh water access, and marine food resources naturally concentrate human populations, a sea level rise of 10 meters over 2 or 3 generations is not a gradual inconvenience. It is a catastrophe that swallows your coastline, floods your settlements, forces repeated migration inland, and fundamentally disrupts the resource base your community depends on. The specific lands submerged by this process were not empty wasteland. Doggerland, the landmass that once connected Britain to continental Europe across what is now the North Sea, was a substantial territory with rivers, lakes, forests, and coastlines that supported human populations for thousands of years before the rising sea finally covered it completely, with the last remnants disappearing around 6000 BCE. Sunderland, the continental shelf of Southeast Asia connecting the modern islands of Sumatra, Java, Borneo and Bali to the Asian mainland, was a landmass roughly the size of India that was progressively submerged as sea levels rose, with the final flooding occurring over roughly 5,000 years. The Black Sea Basin, currently a large inland sea connected to the Mediterranean through the Bosphorus, may have been a freshwater lake significantly smaller than today, until approximately 5600 BCE, when Mediterranean waters broke through the natural dam at the Bosphorus, in an event that some researchers have proposed as the direct historical referent for the Mesopotamian flood traditions, a catastrophic, relatively sudden inundation of a densely inhabited basin. These were the most productive, most densely inhabited, most culturally developed regions of the prehistoric world. Low-lying, coastal, well-watered, biologically rich, exactly the kind of terrain that attracts and sustains human populations, and they are now underwater, sitting under anywhere from a few meters to over 100 meters of ocean, poorly mapped, rarely studied by archaeologists, and essentially inaccessible using conventional excavation methods. Whatever was there, whatever settlements, whatever social structures, whatever knowledge systems those populations had developed over the thousands of years they inhabited those now submerged lands, went with the water. The flood myths, understood in this context, are not mythology in the sense of pure invention. They are the preserved cultural memory of populations who stood on shorelines and watched them disappear, who moved their settlements back from the water as children and watched their children's children move them back again, who carried with them, encoded in the structure of their most important stories, the memory of a world that existed before the water came, a world that is now beneath the sea. The specific details became mythologized over millennia of retelling. The geological process of gradual sea level rise, punctuated by dramatic pulses, was compressed by narrative necessity into the span of a single catastrophic event. The impersonal forces of oceanography and climate were personified as divine agency, because that is how human minds naturally encode and transmit information about events of overwhelming scale. But underneath the personification, underneath the mythological elaboration, the core event is real. A world ended, people survived, and the memory of that ending, carried in the structure of stories told around fires for hundreds of generations, outlasted every physical trace of the world that was lost. Memory survives where physical evidence cannot. And memory, transmitted with the careful fidelity that oral cultures at their best are capable of, may be preserving the outline of something that the geological record swallowed whole, and that we are only now, with the tools of modern paleoclimatology and marine archaeology, beginning to dimly reconstruct. Part 14. The pattern. Let us now pull back. Let us lay out everything we have covered tonight and look at it together from a distance, the way you might step away from a painting that only makes sense when you stop examining the individual brushstrokes and let your eyes find the whole image at once. We have been moving through a lot of specific detail: isotope ratios, erosion profiles, sediment cores, pillar weights, carbon petagrams, and detail is necessary, because detail is what separates a rigorous argument from a feeling. But we've arrived at the point where the detail needs to give way to the pattern, and the pattern is what I actually want to talk about. Here is what we have assembled tonight, laid out plainly. We have a geological record that becomes ambiguous beyond roughly 1 to 2 million years ago in its ability to distinguish industrial chemical signatures from natural geological events, a limit established not by conspiracy or negligence, but by the straightforward physics of how rock forms, transforms, and erases information over time. We have the Paleocene-Eocene Thermal Maximum, an event 56 million years ago whose carbon isotope signature mirrors our own industrial output in the ways that matter most for detection, whose trigger remains genuinely unresolved after 3 decades of intensive study, and which demonstrates beyond reasonable doubt that events producing signatures indistinguishable from industrial activity can arise from entirely natural causes. We have the Younger Dryas onset, an event 12,800 years ago that disrupted human civilization at the moment it was beginning to form, whose trigger is actively contested between a meltwater pulse hypothesis and a cosmic impact hypothesis with no clear resolution in sight, and which demonstrates that catastrophic events of sufficient scale can erase archaeological records, break chains of cultural transmission, and reset developmental trajectories in ways that make before and after look like 2 entirely different stories. We have Göbekli Tepe, a monumental construction site 11,500 years ago that appears in the archaeological record without a clear preceding developmental sequence, built by people who should not, according to every model we had previously constructed, have possessed the social complexity required to produce it. We have the Sphinx erosion debate, a contested geological interpretation of physical evidence on one of the most studied monuments in human history, in which a credentialed geologist and the mainstream archaeological community have been disagreeing for more than 30 years without resolution. And we have more than 500 global flood myths, distributed across every inhabited continent, preserving with remarkable structural consistency a memory of catastrophic inundation that correlates precisely with real, geologically documented events confirmed in at least some cases by the independent evidence of submerged landscapes, and Aboriginal Australian oral traditions accurate to 10,000 years. That is the inventory. Now I want to be very precise about what this pattern means, and equally precise about what it does not mean, because the difference matters, and I think you deserve the honest version, rather than the version that tells you what would be most satisfying to hear. Taken individually, each of these anomalies has a plausible explanation within the framework of conventional science. The PETM was caused by a combination of large-scale geological processes, volcanism, methane hydrate feedback, possibly orbital forcing, operating in a cascade that amplified their combined effect. The explanation is incomplete in its details, but not implausible in its broad outlines. The younger Dryas was caused by disruption of North Atlantic thermohaline circulation, possibly triggered by meltwater pulses from deglaciating ice sheets, possibly complicated or accelerated by a cosmic impact event, possibly both operating together. Göbekli Tepe was built by hunter-gatherers who are more socially complex than our previous models had assumed, possibly motivated by the construction process itself to develop the agricultural practices that supported it. The Sphinx erosion reflects the complicated geology and climate history of the Giza Plateau, including subsurface moisture movement, differential weathering of heterogeneous limestone, and the occasional intense rainfall events that do still occur in the region. The flood myths reflect a real and geologically documented catastrophe, the post-glacial sea level rise that submerged coastlines worldwide between 19,000 and 7,000 years ago, processed and preserved through the remarkable machinery of oral cultural transmission. Every one of these explanations is defensible. Every one of them is held by credentialed, serious researchers. None of them requires invoking anything outside the boundaries of established science. I want you to hold that in one hand. Now let me tell you what to hold in the other. Taken collectively, these anomalies form a pattern, not a random scatter of unrelated puzzles, but a series of gaps and ambiguities concentrated in exactly the places where we would expect to find evidence of something unusual if it had existed, and critically also in the places where we would most expect evidence to be degraded, ambiguous, and resistant to clean interpretation. The PETM sits at 56 million years ago, well beyond the detection horizon that Frank and Schmidt identified. The younger Dryas sits at the precise moment in human history when civilization was forming, the moment whose archaeological record would be most disrupted by a catastrophic reset. Göbekli Tepe appears at the exact boundary of the post-glacial period, in the region where the flooding of coastal Sunderland and the Mediterranean basin would have been most disruptive to any existing coastal populations, potentially forcing inland migration that brought knowledge and social complexity into territories where the archaeological record had not previously shown it. The flood myths preserve a memory of exactly the geological process that would have been most catastrophic for any coastal civilization in development during this period. The Sphinx sits at the intersection of a contested geological timeline and a period of African climate history that mainstream archaeology has not yet fully integrated into its reconstruction of early Egyptian prehistory. These are not randomly distributed anomalies. They cluster around the same periods, the same mechanisms, and the same epistemological boundaries that the Silurian hypothesis identified as the zones of maximum uncertainty in our reconstruction of the past. Whether that clustering is meaningful, whether it reflects something real about the history we cannot yet see, or whether it is a product of confirmation bias, of our tendency to notice and connect data points that fit a pattern we're already looking for, is a genuinely important question. I am not going to answer it for you, because I don't think I can answer it honestly, and giving you a false certainty in either direction would be a disservice. Here is the line I want you to carry with you, the one sentence that I think captures what tonight has actually been about. The pattern is not proof, but the pattern is real. These anomalies are not invented. The scientific debates surrounding them are not fringe discussions conducted on internet forums by people with no credentials. The uncertainty they represent is not manufactured by motivated reasoning or wishful thinking. Frank and Schmidt's paper is not a conspiracy document. It is a careful, responsible, methodologically sound inquiry into the limits of geological detectability, published after peer review in an established scientific journal, conducted by researchers whose mainstream credentials are unimpeachable. The PETM is one of the most intensively studied geological events in Earth's entire 4.5 billion year history, precisely because of its relevance to modern climate science. The Younger Dryas debate involves hundreds of researchers across multiple disciplines and has generated thousands of published papers over 4 decades. Göbekli Tepe is one of the most celebrated and consequential archaeological discoveries of the 20th century, reshaping our understanding of prehistoric human complexity in ways that are still being worked out. The flood myth research draws on the combined work of anthropologists, folklorists, geologists, and oceanographers across more than a century of comparative study. These are not marginal data points. They are central, mainstream, actively researched questions, and they all converge on the same uncomfortable realization. Our knowledge of Earth's past is less certain and less complete than we usually allow ourselves to admit. That admission is not a defeat. It is not an invitation to abandon rigor and believe whatever feels compelling. It is, if anything, the most scientific statement you can make about the state of the evidence, because science is not the accumulation of certainties. Science is the honest accounting of what the evidence supports, what it doesn't support, and where the boundary between those two territories actually lies. Pretending that boundary doesn't exist, or that it sits further back in time than it actually does, is not scientific confidence. It is scientific overreach. And overreach, in either direction, claiming too much certainty that something existed, or claiming too much certainty that nothing could have, is the same failure of intellectual honesty wearing different clothes. The honest response to this pattern is not to conclude that a prior civilization definitely existed. That conclusion is not supported by the evidence, and saying so clearly matters. But the honest response is also not to dismiss the question as obviously answered, to treat the absence of definitive proof as proof of definitive absence, or to mistake the confidence of our assumptions for the strength of our evidence. The honest response is to hold the question more carefully, to sit with the uncertainty rather than collapsing it prematurely into a comfortable answer that lets you stop thinking about it. To recognize that the gaps in our knowledge are real gaps, not failures of imagination, not fringe speculation, but documented, peer-reviewed, actively debated uncertainties at the heart of our reconstruction of this planet's past. Science doesn't require certainty to be science. It requires honesty about the boundaries of what the evidence can support, and tonight, if nothing else, I hope we have moved those boundaries a little closer to where they actually are. Part 15. The Mirror. And now we turn the lens around. We have spent the majority of this evening looking backward, trying to understand what the geological record can tell us about the past, what it can't tell us, and what that gap in our knowledge means. But there's a different way to approach this question, and it's the one that I find genuinely strange to sit with once you follow it all the way through. Consider what we're doing right now. In the year 2026, the human industrial civilization has been injecting carbon dioxide into the atmosphere at rates that have no geological parallel in the last 56 million years in terms of speed, though not yet in total magnitude. We have released roughly 580 petagrams of carbon through industrial activity since the early 1800s. We are generating that output at approximately 10 times the peak injection rate of the PETM. We have distributed microplastics across every environment on the planet, from the deepest ocean trenches to the snowfields of the Himalayas to the stomachs of animals that live in regions no human has ever visited. Microplastics are a class of material with no natural source or analogue, and they are now so ubiquitous that they appear in virtually every sediment sample collected anywhere on Earth. If you pull a sediment core from a lake or ocean floor and look at the layers, you will find a distinct sharp boundary, a line below which no microplastics appear and above which they are suddenly everywhere. That boundary corresponds to the mid-20th century, It is, in geological terms, a crisp, unambiguous marker of our presence. Future geologists will be able to find it in the record. We have produced and distributed radioactive isotopes that do not occur naturally in significant concentrations. The atmospheric testing of nuclear weapons between 1945 and 1963 produced a global spike in certain radioactive isotopes, particularly cesium-137, strontium-90, and carbon-14, that is clearly visible in ice cores, sediment layers, tree rings, and biological samples from around the world. Like the microplastics layer, the nuclear fallout layer is a sharp, globally distributed marker that will be detectable in the geological record for thousands to hundreds of thousands of years. We have created entirely new minerals. Roughly 200 new mineral species have been identified that formed exclusively as a result of human industrial activity. Minerals that could not have formed through any natural process, that exist in the geological record solely because we were here. Future mineralogists examining rocks from our era will encounter substances with no natural precedent. The formal recognition of all this in the scientific community is the Anthropocene, the proposed geological epoch defined by human influence on Earth systems. The Anthropocene Working Group, an international scientific committee, spent years debating when exactly to define the start of the Anthropocene and concluded that the mid-20th century, specifically around 1950 to 1960, is the most clearly defined boundary, coinciding with the great acceleration of industrial activity, the nuclear fallout layer, and the beginning of mass microplastic distribution. So here is the thought experiment that closes our evening. Imagine a geologist 56 million years from now. She, or it, or whatever form intelligence might take by then, is examining a sediment core from what was once a continental interior. She's working through the layers methodically, cataloguing the chemical signatures, the pollen records, the isotopic ratios, the microfossils, and she comes to a layer, the Anthropocene layer, that contains the following signatures: a negative carbon isotope excursion of several per mil, coinciding with a sharp temperature increase in the climate proxies, a globally distributed anomalous spike in certain radioactive isotopes, a thin, globally distributed layer of synthetic polymer fragments, an anomalous concentration of rare earth elements inconsistent with the local geological background, a brief, sharp pulse of atmospheric methane, and then, a few tens of thousands of years later in the record, all of those signatures fading back toward background as whatever happened resolved itself. What would she conclude? She would have better tools than we do today, tens of millions of additional years of geological science and technological development. But she would also be looking at a record that has been subjected to 56 million years of additional geological processing. The plastics may be unrecognizable. The radioactive isotopes will have decayed through multiple half-lives. The artificial minerals may have been recrystallized by pressure and heat. The negative carbon isotope excursion, that might still be there, faded and compressed, a ghost of a signal in a noisy record. Would she see us? Or would she see an anomaly, real, measurable, but attributable to any of a dozen natural mechanisms? Would she write a paper proposing a geological explanation for a carbon spike that has no other clear analogue in the record? Would her colleagues dispute the interpretation for decades? Would a small group of outliers propose something wild, something that, if they were wrong, would be career-ending, only to be dismissed? We have spent this entire evening building the case that the geological record is incomplete, ambiguous, and systematically degraded by the planet's own physical processes. We have shown that the signatures of industrial activity are, in important ways, similar to the signatures of natural geological events. We have shown that catastrophic events can erase civilizations from the record and reset cultural trajectories. We have shown that even the monuments and artifacts of historical periods are subject to contested interpretation. And we have shown that 56 million years ago, something happened that left a mark in the rock that looks, in important ways, like what we are leaving right now. The Anthropocene layer is us. It is our signature. It is the most unambiguous evidence of our existence that future geologists will have, and even it, given enough time and geological processing, becomes ambiguous. Even it, at the resolution available through tens of millions of years of rock, starts to look like something that natural processes might produce. So we arrive at the final question, the one that has been waiting at the end of this thread all along. It's not really a historical question anymore. It stopped being a historical question somewhere around the time you started thinking about what that future geologist would actually see in the rock. The question is this: if we, with our cities, our carbon emissions, our microplastics, our nuclear weapons, our 200 new minerals, our global infrastructure, if we could become ambiguous in the rock record within a few million years, what does that say about everything that came before us? What does it say about the 100 million years before the PETM, and the 100 million years before that, and the billions of years of complex Earth history that preceded the first unambiguous fossil evidence of anything we would recognize as life? The Earth has been running this experiment for 4.5 billion years. It has had complex chemistry, liquid water, and active geology for most of that time. We have clear, reliable records for an extraordinarily small fraction of it. For the rest, the vast majority of the planet's history, we have inferences, models, degraded and ambiguous signals in deeply processed rock, and the honesty of scientists like Frank and Gavin Schmidt, who are willing to say out loud that our tools for looking backward have limits. We don't know as much about this planet's past as we think we do. That's not a conspiracy. That's not pseudoscience. It's a statement that two mainstream NASA scientists published in a peer-reviewed journal in 2018, and that the entire field of geology implicitly supports every time it publishes another paper revising our understanding of what happened and when and why. The question that haunts this entire evening is not, was there something here before us? We cannot answer that. We cannot know it. The record is too incomplete, too ambiguous, too thoroughly processed to give us certainty in either direction. The question that actually matters is quieter than that, and in some ways more unsettling. It is, what does it mean to be a civilization that cannot confirm it was the first? Because if we cannot confirm it looking backward, then we are by definition building the same ambiguity into the record for whatever might come after us. We are the potential PETM for a geologist 56 million years in the future. We are the anomalous layer. We are the carbon spike with the puzzling trigger. We are the moment in the record that the textbooks will debate. And maybe, if we're lucky, if the planet is lucky, if something survives to do the debating, those future scientists will be as careful and as honest as Frank and Schmidt. Maybe they'll write a paper. Maybe they'll name it after a television show to signal that they know how strange the question sounds. Maybe they'll conclude, carefully and methodically, that they strongly doubt anything industrial caused the anomaly in the early 21st century layer, but that they cannot rule it out. And maybe, somewhere in that future equivalent of a peer-reviewed journal, the question will sit quietly, the way it sits tonight in the International Journal of Astrobiology. Unanswered, unanswerable, but honest. Are we the first, or are we the second try? I genuinely don't know, but I'm not sure we should be as comfortable with obviously the first as we've been.